we see almost nothing except that one peak of interest. Now, anytime that we see a peak of interest in the chromatogram, we can double click and we can see the mass spectrum. And so here we see the mass spectrum. The molecular ion is 348. That probably would be the most unique diagnostic ion, but it's very small in the electron impact spectrum. So maybe 311 is a more sensitive ion to monitor if you're doing selected ion monitoring. Well, the components in an instrument are sample introduction, ionize that sample, separate it, and then detect those separated masses. So I've listed some of the inlets and some of the methods that we use in mass spectrometry. DIP, DEP, I've got a picture I think in the next slide. That stands for direct introduction probe or direct exposure probe. That's a way to introduce a sample directly into a GCMS without going through the GC. So sometimes I call that the poor man's LC-MS interface. You can separate components on an HPLC, take a component that's moderate polarity, it doesn't decompose very rapidly at high temperatures, put it in the direct probe, flash vaporize it into the mass spectrometer, and actually get molecular ions. Of course, the GC is a very common inlet for mass spectrometry, as is HPLC, and we see variable acceptance of capillary electrophoresis as an introduction method. CE and mass spectrometry are not natural friends, and so we kind of have to force them to be friends. And sometimes people think it's worth the effort, sometimes they don't. The ionization methods, those people that have done GCMS will recognize EI or CI, electron impact, chemical ionization. For LCMS, we use different techniques. All of these techniques are at atmospheric pressure. It means that we spray the eluent from the HPLC into the ion source at atmospheric pressure, and electrospray or nanospray, the ions are actually already existing as ions in the liquid phase, and all we do is desolvate those ions. In atmospheric pressure chemical ionization and atmospheric pressure photoionization, we actually vaporize the solvent and pump it away, and then use either UV light or Townsend discharge chemical ionization to ionize the analytes that are left over. These are generally non-polar molecules that we use these techniques for, and electrosprays for polar molecules. Mass separations, magnetic sector was the first mass spectrometer. Our factory in Bremen, Germany has been building magnetic sector instruments continuously since 1947. Time of flight has been around since the 60s. Ion trap we introduced in 1982. This was an invention brought to market by Thermo, as is quadrupole. The very first single quadrupole and the very first triple quadrupole were both also from what was then called Finnegan, is now a part of Thermo Scientific. FTICR, again, this was a product that was brought to market first by a Thermo company. In this case, where's Ken? He's not here for his one moment of glory. FTICR was actually first commercialized by Nicolay. The Orbitrap is an invention that has been created from the beginning in research by Thermo, and so we have literally dozens of patents, and nobody else then builds an Orbitrap. And then we have a number of hybrid instruments where we put together two or more of these mass analyzers into a complicated MS-MS kind of instrument to give us a lot of different choices for the data that we want to mine from a complex mixture. The most usual detection system is an electron multiplier. Very often it will have a conversion dynode in front of it to give us higher responses for higher mass molecules. The photomultiplier is actually only used by one company, and that there's an interesting history there. Ask me sometime, I'll tell you the history behind that. But it has to do with the violation of patents and finding a way around it. Microchannel plates are kind of like multiple electron multipliers stacked together, and that's what's used in time-of-flight detection systems. In FTMS, Fourier transform mass spectrometry, we don't have a particle detector. We don't actually collide the ions into any kind of detector. We know that those ions are present because they're circulating inside of an electrode and creating an image current. And we read that image current as a frequency, convert the frequency to mass, and when we have multiple masses, we first use a Fourier transform to separate the individual frequencies into individual mass numbers. So here's a picture of that direct exposure or direct introduction probe. The difference is the DEP. You probably can't see it out there, but there's a little rhenium wire right here above this ceramic insulator, and you actually dissolve your sample in a volatile solvent, acetone or ether, and let it evaporate. The particles are deposited on that little wire, and you push that wire into the front of the instrument that is right here. And now you flash vaporize the sample. This